Hello everyone. The title of this video is Find the Domain of a Radical Function. All right. Now every question, every exercise or example that I'm doing in this video is taken directly from a free online textbook at openstax.org, and it's their Intermediate Algebra 2nd edition text. I'll be working under the heading Find the Domain of a Radical Function. I'm going to be working on only the even numbered exercises, so starting with 368 and going to 370 to 372 and so on. You may notice that the odd numbered exercises have a link on them, which if you click on, you'll be taken to the solution. So I'll be working on just the ones that don't have a solution available. And I will also have timestamps for each example in the description of the video. Alright, so if you look at the description, you'll see example 1's timestamp. That'll be for number 368, example 2 for number 370, example 3 for 372, etc. Alright, for all the even numbered problems up to 382 for this video. So if you want to bounce around to see specific questions, go ahead. Alright, and one final request I would make of you is that whenever I bring up a new question, pause the video and try to work on it yourself. See how you do. And then watch me do it and compare your work to mine. Because if you're just watching me do these things, without practicing yourself, chances are you're not going to learn all that much. Okay, so the first question is exercise 368. I have these written out. And in every single one of these questions, we're asked to first find the domain of the function, and secondly, write the domain in interval notation. Alright, so the domain of a function, recall, is the set of all allowable inputs for that function. And I'm hoping you have seen or recall interval notation from other videos I've put up, or from your reading and studying yourself. Alright, so example 1, which again is exercise 368 from the text. We're given this function called little f of x, right? The input variable is x, and then f of x represents the output, and then over here is how you calculate the output, right? You take 4 times the input minus 2, right? 4 times the square root of 4x minus 2. Alright, so remember, for even roots, right, this is an even root, a square root, right? Square roots, fourth roots, sixth roots, etc. I've been calling even roots. So remember, for an even root, the radicand, right, the expression, right, the number inside the root, this can't be negative if we're talking about having a real number output, right? I'm going to input a real number x. I would like the output to also be a real number. And hopefully you recall that an even root of a negative number is not real. So this can't be negative, right? This expression 4x minus 2, this radicand, the radicand can't be negative. Right, so that leads me to the following statement. That means that the radicand 4x minus 2 has to be greater than or equal to 0. That's what it means to be non-negative, can't be negative. It means you have to be positive or 0. So for any of these even root functions, I'm going to set up an inequality like this, where we have the radicand has to be greater than or equal to 0. And then we solve this, and that'll be our domain. Those will be the allowable values for x, the allowable inputs. So I would add 2 and then divide by positive 4, so the inequality won't change. So x has to be a number greater than or equal to 2/4, which reduces to 1/2. Right, and here it is. Here's a description of our domain. Now the way we write the domain, we can do it in a couple ways. Right, from this I would say that, okay, then the domain of f, right, the domain of this function f is, now one way you can write it is in what's called set builder notation. A little curly braces to start the set. And the input variable here is x, so it's all x such that, right, a little bar or a colon, I can plug in any x I want as long as it's greater than or equal to 1/2. Right, if I plug in a number less than 1/2, that'll be bad. Right, I'll have the square root of a negative number, which is not real, if I plug in a number less than 1/2. Right, so I'll put this in a circle. There's part 1. Right, find the domain of the function. Right, I can plug in any value 1/2 or greater. Part 2 is write this domain in interval notation. So let's say this number line here represents values of x. Right, it represents like the x-axis, or again just values of x, a number line. And I'll put, here's 1/2. Let's say 1/2 is right here on the number line. We can use values equal to 1/2. So I'm putting a closed point on this, right? Not an open point. So 1/2 is in the domain, and all the numbers greater than 1/2. So all these numbers here to the right of 1/2 are also in the domain. So here's a picture of the domain on a number line. Right, here's a picture of the domain. And I feel like once you have a picture of a set on the number line, it's easier to write that set in interval notation. Now remember, interval notation you're always going left to right, low numbers to high numbers. So here I would say that the domain of f is the following set, but written instead of set builder notation, I'm writing it in interval notation, going left to right here. Start at 1/2, so I write 1/2, then comma, and then where does this set of numbers end? Well, it doesn't end as I go from left to right, so I'm going to indicate that by writing positive infinity. And then on each end you put either a bracket or a parenthesis, depending on whether those numbers on the ends are included. 1/2 is in the set, 1/2 is in the domain, so you do a bracket, right? One of these rectangular brackets here. If it wasn't in the domain, I would put a parenthesis, right, a nice rounded off parenthesis. Now infinity, right? Infinity is not a number. Infinity is an idea, so it doesn't technically belong to the set. So always parentheses on infinity or negative infinity. And there's the answer to part 2. Right? The domain of this function is all the numbers from 1/2 to infinity, right? All the numbers greater than 1/2 or equal to 1/2 itself, right? That's why I got the bracket on there. Great. All right. So now what I want to do is show you a picture of the graph of this function on a graphing calculator. In a later video we'll draw some of these graphs by hand, but for right now I just want to show you a picture of the graph of this function, on a graphing calculator. And you'll see that the only ordered pairs, the only points on the graph, are going to have x values of 1/2 or greater. Right? So going back to websites here, I have this free online graphing calculator pulled up. It's at desmos.com. And I'm sure I've shown you this in previous videos, again, if you've been following along with other videos of mine. And you can just very easily enter the function we were given here. F of x equals the square root of 4x minus 2. And you see this graph? See how there aren't any points to the left of this point here. And you see this point has the input, has an x value of 1/2, 0.5. And all the other points on the graph, right, have an x value greater than 1/2, right? 5.39, 6.48, 7.62, blah, blah, blah. Right? As I move points along this graph, see all the x coordinates are greater than or equal to, right, 1/2, right, when you get down here. But notice there are no points to the left of this x equals 1/2. Right? There are no points on the graph with an x value less than 1/2. And once again, that's because if I plugged in anything less than 1/2 for x, I'd be taking an even root of a negative number, and I would not get a real number output, right? The x-axis and y-axis represent real numbers only. Right? Great. So we can say the domain is x values from 1/2 and greater, right? Greater than or equal to 1/2, as I said back on my paper. Wonderful. Okay. So I hope that made sense looking at the picture there. Right? Domain, all the x values used are 1/2 or greater. All right. Next question. Number 2. Exercise 370 from the text. Same thing, same instructions for every single problem. We have the function g of x equals the square root of 8 minus x. So once again, I have an even root. So just like question 1, the radicand can't be negative. So to help me find, what values I can use for x, take the radicand, right? Take 8 minus x, the expression underneath the symbol, and say, hey, this has to be greater than or equal to 0, right? It can't be negative. And then I solve this inequality. So you're going to be setting up an inequality like this, for any even root function. Then I could simply add x and then switch sides. We get x is less than or equal to 8. Right? So the domain of this function g, right, the domain of g is, I can plug in any value for x I wish, as long as x is a number less than or equal to 8. Right? Because if I plug in a number greater than 8, I'll be taking an even root of a negative number, and that's bad. That's not real. Right, and there we go. This is it. This is part 1. What's the domain of the function? I can plug in, 8 or any number less than 8 for x. And then the interval notation, right? And you can draw a picture if you wish, right? But if you're familiar with the number line, if you're familiar with interval notation, you shouldn't have to. But I'll do it one more time here. Right? Here's a number line. Say this number line represents possible values of x, possible values of the input. Say the number 8 is here. And we're saying we can plug in 8, right? So 8 is in the domain. I put a closed point above that. Right? I would put an open point if it didn't belong. And then any value less than 8, right? So 7, 6, 5, all these numbers to the left here. Though there's a picture of the domain on a number line. Well, if I'm writing an interval for this picture of the domain, well, there is no left end to this, so we're starting at negative infinity, comma, and then this goes all the way up as you go left to right up to 8. Always parentheses on infinities or negative infinities, and then 8 is in the domain. So a bracket, right, rectangular bracket, and there's the second half of what they wanted, right? They want the domain stated and also the domain stated in interval notation. Okay, and then once again I'll show you the graph of this function, and you're going to see that every point on the graph will have an x value of 8 or less, right? Let me do that, right? So I'll enter, we had g of x equals the square root of 8 minus x. And you see this green graph, all these ordered pairs popping up. And you see this point has, 8 comma 0 has an x coordinate of 8. And then as I move along the graph, see how every single x coordinate, is less than 8, 4.93, 2.71. There's, 0, x value of negative 1.6, negative 1, negative 2, negative 4.44, negative 6.63. Right, but every point on the graph has an x value of 8 or less. Right, has an x value less than or equal to 8. And that's the domain, right? The domain is all the x values, all the inputs that are allowed. And notice if I move to the right here, there's no graph to the right of 8 on the x-axis. Right? Because if you plug in a value greater than 8, you'll be taking the even root of a negative number. And that's, a non-real output, which won't show up on the graph on the xy plane. Okay? Wonderful. Hope that made sense. All right, next question. So number 3 corresponds to, exercise 372. All right, so we have h of x equals, and it's another even root, the square root of 6 divided by x plus 3. All right, so this one has an even root, and it has a denominator with a variable in it. Remember, denominators can't be 0. All right, so that tells me right away that, x plus 3 can't be 0, meaning that x cannot be equal to negative 3. All right. So this is one condition on my domain, right? X can't be negative 3, and also the radicand can't be negative, right? So 6 divided by x plus 3 has to be greater than or equal to 0. Right, setting up the same kind of inequality I've been doing with these other square root functions, right, in number 1 and number 2. And then solving this. Now, this is one of those rational inequalities. Hopefully you recall, I've done videos before on solving rational inequalities. Here's a number line representing values of x. Remember, first I put up the critical values, right? What makes the numerator of this, I've got a fraction on one side, 0 on the other, like we want. And then, are there any values that make the numerator 0? No, that's always 6. Any values that make the denominator 0? Well, yeah, negative 3. So I'm going to mark off negative 3 here, and just indicate real quick that that's not going to be a solution, because, x can't be negative 3. So I'm putting an open point above negative 3. That means negative 3 is not a solution. And then I'm just going to take all these critical values and plug in values around them. Plug in negative 4. You'd have 6 divided by negative 1, which is negative 6. Is negative 6 greater than or equal to 0? No, it's not. So there aren't any solutions to the left of negative 3. And how about to the right of negative 3? Well, how about 0? Right? Plug in 0. You'd have 2 is, 6 divided by 3 is 2. 2 is greater than or equal to 0. Yeah. So all the solutions are this way. The solutions of this inequality are to the right of negative 3, for values of x. All right, so again, the solutions of this inequality here are values of x that are simply greater than negative 3. Right, x has to be a number greater than negative 3 to make that true. And then putting these together, we get our domain. Right? So the domain of this function called h is all x values as long as x is greater than negative 3. Right? As long as x is greater than negative 3, we're fine. Right? Can't be equal to negative 3. Right? Using that because that'll make a denominator 0. You can't divide by 0 ever. And can't be less than negative 3 because if you plug in a value less than negative 3, you'll have the square root of a negative number, which is not real. Right, so the only values I'm allowed to plug in here to get a real number output is negative 3, is greater than negative 3. So there's the domain, written in set builder notation, but also the domain of h. They also want me to write this in interval notation, which would be, I have a picture of it right here. Right? All the numbers greater than negative 3 are pictured right over here. That's going from negative 3 to positive infinity, but parentheses on negative 3, right? Negative 3 is not in the domain, and always parentheses on the infinities. And there's, now it's the same set of numbers, right? Both things I've circled here, they're the same set of numbers, just in different notation. All right, and then once again, I like to go and check my work. Go to the Desmos graphing calculator. I'm going to enter this function that we were given, h of x equals the square root of 6 divided by x plus 3. And look at this, right? Now, look at x. I'm going to put in the line x equals negative 3 as well. And you're going to see what's called a vertical asymptote. And I'll make this dashed. You can hit the little edit list and change it to a dotted line instead of a solid line. Right. And I'll hit done. And you see what we have here is called a vertical asymptote. Right. The graph, the purple graph, gets closer and closer to that vertical line, the dotted line there, but never actually touches it. Right. You can go, because x can't be negative 3. Right. There's x equals negative 3. There will not be a point of the graph on this dotted line, because x can't be negative 3. Right? But notice, every point on the graph, the purple graph, right, has an x value greater than negative 3, just like we said on paper. Right? 5 and 5.46 and 6.8 and negative 1.8, negative 2.51, negative 2.66, whatever. Every point on this purple graph, right, the graph of the function h, has an x-coordinate greater than negative 3. Notice, again, there's no point that has an x value equal to negative 3, and there are no points with an x value less than negative 3. There's no graph over here. So our domain seems to be correct. Wonderful. All right, next question. All right, number 4, exercise 374, same deal. All right, same deal. I got the f of x equals another even root, another square root of x minus 1 divided by x minus 4, another fraction in the radicand. All right. So once again, there's a denominator with a variable. So x plus 4, right, this denominator of this fraction, this can't be 0. And that leads me to the statement x can't be negative 4. Right, so that negative 4 can't be in the domain. It's not allowed because you can't divide by 0. All right, and also the radicand, right, this expression underneath the even root, the square root here, x minus 1 divided by x plus 4, has to be non-negative, right? It has to be greater than or equal to 0. And we're solving this inequality. Alright, so just like in the previous one, right, this is another one of those rational inequalities where I have a fraction on one side, 0 on the other, and I'll just start drawing a number line down here. Alright, and this number line represents, possible values of x. And on this number line, I'll mark off, the critical values. What for this fraction, what makes the numerator 0? Well, that would be x equals 1. So I'll mark off 1. And what makes the denominator 0? That would be negative 4, right, which would be to the left of 1. Alright, and then now 1 itself, 1 is a solution, right? If I plug in 1, you'd have 0 divided by 5. 0 on the left is greater than or equal to 0, right? It satisfies the equal to part. So 1 is a solution to this inequality. So I put a closed point above it, a dot. Negative 4 is not. We just said a second ago, right? If I plug in negative 4, you're dividing by 0. That's bad. So I'm going to put an open point right above negative 4. Negative 4 is not a solution. All right, so now these critical numbers, negative 4, positive 1, right, they break up the number line into 3 intervals. Numbers to the left of negative 4, between negative 4 and 1, and to the right of 1. So I just pick a number from each of them. All right, so how about negative 5? All right, if I plug in negative 5, does it satisfy this? Now negative 5 minus 1 is negative 6. Negative 5 plus 4 is negative 1. You'd have a positive number. You'd have positive 6 on the right. Is that greater than or equal to 0? Yes, it is. So the numbers to the left of negative 4 are solutions, so I'll indicate that. All right. So all these numbers to the left of negative 4 forever are solutions of this inequality. Now how about between negative 4 and positive 1? Well, 0's in between there. That'd be an easy one to pick. If I plug in 0 for x, you'd have negative 1 over 4. Negative 1/4, is that greater than 0 or equal to 0? No. So this interval between negative 4 and 1 doesn't have solutions. And then pick a number to the right of 1, say 2. 2 minus 1 over 2 minus 4, that'd be positive 1/6, which is positive. That's greater than or equal to 0. So yes, all these numbers to the right of 1 are also solutions. All right. So the domain, basically we have the domain pictured here. Here are all the values I'm allowed to plug in for x in this function. Values, less than negative 4 but not equal to negative 4. Or, right, or usually when there's a gap, right, or 1 or greater, right, values 1 or greater. So again, I'll write the domain in 2 different ways, right? The domain of f is, any value of x I wish, as long as x is less than negative 4 or x is greater than or equal to 1. Right. Just drawing the inequality that represents this picture, right? The solutions of this statement here. Right. Wonderful. Yeah, so I'll box that one in, right? That's part of our that's the first part of our answer, right? Stating the domain in some way. And then the second part, right, is stating the domain in interval notation. So this is the same set, right? It's still the domain of f, means it's the same numbers as these. And I've got my picture of the domain right here. First interval is from negative infinity up to -4, but parentheses on the -4. And then union for the gap, right? The union symbol represents the word or in set notation. And then the second interval, the second piece of the graph here, the second piece of the domain is from 1 to infinity, right? 1 to infinity, but a bracket on the 1, right? 1 is in the domain. I am allowed to plug in 1 for x here. Right, and there you go. There's the domain of this function written in interval notation. Great. And then once again, I'm going to go to the Desmos site and we'll take a look at this. So I have f of x equals the square root of x plus 1, no, x minus 1, sorry, divided by x plus 4. Alright. And I'm going to actually put up x equals -4 as a vertical line and x equals 1. And you're going to see, let me just make these the same color and dash them in. Make them dotted lines. And hopefully you see that our domain is correct, right? We said the domain of this function was values of x, less than -4, and you see this piece of the graph over here where all the x coordinates are less than -4, right? You see -6.18, -7.2, right? -4.21, and we have a vertical asymptote here, right? The graph gets closer to this vertical line x equals -4, but never actually touches it. Right, you see, still on the graph, all the x coordinates are less than -4 there. And then, 1 or greater, right? There's a point on the graph with an x coordinate of 1. And then all these points over here have an x coordinate greater than 1. Right? So the domain we wrote was correct, right? X values less than 4 are allowed, less than -4 are allowed, and x equals 1, and anything x greater than 1 is allowed. And notice that in between these two vertical lines I put up, in between x equals -4 and x equals 1, there is no graph. Right? There is no graph in between these two vertical lines in this band here. And that again fits with our domain that we wrote. Right? And also, if I were to plug in any value between -4 and 1, we'd be taking the square root of a negative number, and that wouldn't be real. That's why there's no graph there. Alright, so I double checked my work here with this calculator. It looks like I'm good. Wonderful. Alright, next question. Alright, so far we've seen a bunch of even roots, right? Square roots. Now in number 5, which corresponds to exercise 376, we have a cube root. Right? G of a function called g of x equals the cube root of 6x plus 5. So this is an odd root, right? Cube root, fifth root, seventh root, etc. And I'm telling you right now, these are easy, right? You've seen these before. For an odd root, the radicand, right, the expression inside the root, the radicand can be any real number. So the radicand can be positive. It can be negative. You can take the cube root of a negative number and the result will be real. And it can be 0. So these odd root questions, when they're asking about the domain, are very, very simple. The domain of this function is any x value as long as x is x is a real number. Now you could write it this way, or you could just say that the domain is all real numbers, right? But you can plug in anything for x, and the output will be real. So very simple for these odd root functions. All right, and the interval notation for this, you may recall this from a previous video as well, right? The domain of G is, you're going, if you're doing you can plug in anything on the entire real number line. So that's from the far left, right, from negative infinity to the far right, right? So from negative infinity to positive infinity, and always parentheses on the infinities. Okay, great. And once again, I'll go to the Desmos site. We'll enter this function. All right, so g of x equals, now if you want to enter the cube root symbol, you have to bring up this keyboard here, this keypad, go over to functions and miscellaneous functions, and then they have the nth root here, and then you have to enter the index of 3. Let me get rid of the keypad now. So there's the cube root of 6x plus 5. All right, and you see this graph showing up here. Now look at this. See how there's no area on the graph? I mean, you can keep zooming out, zoom out, zoom out, zoom out. There's no area of the graph where there's something missing, where there's a gap. Right? There's a piece of graph everywhere. So see, x value is like negative 53, negative 40 something, negative 30, 20, blah, 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 and then positive, 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 positive. All right, so like every x value is used in some as the x coordinate of some point on this graph. Okay. So we see from the graph on Desmos here that the domain is all real numbers. Wonderful. Okay. Next question. Number 6 is exercise 378 in the text, and it's the same as number 5. It's f of x equals another cube root function, an odd root. Cube root of 6x squared minus 25. And once again, there aren't any denominators, right? That's another. Remember, that's another thing you have to worry about. The denominators can't be 0. You can't take even roots of negative numbers, right? Those are things you're worrying about when stating the domain. But if it's an odd root, and there aren't any denominators with variables, then once again the domain of this function is all real numbers. I can plug in any x I want, right, as long as x is a real number. So you can write it this way if you wish, like I did up there. Or just say that the domain is all real numbers in words like that. And if you're doing interval notation, right, once again, the interval notation for all real numbers, the entire real number line would be from negative infinity to infinity, like this, with the parentheses on the ends. If you want to, let's verify this. Let's enter this function on our calculator. All right, so here we have, it was f of x equals, now you can do the cube root symbol again, or just put the radicand, 6x squared minus 25 raised to the 1/3 power. Remember, the 1/3 power was the cube root. And this is a funky looking thing, right? A cube root of 6x squared minus 25. But either way, no matter how far you zoom out, you'll see that there's no gap in the graph. There's no place where the graph doesn't have a point, right? And every x value is used. Every x value So we can very clearly see from the graph here too that the domain of this function is all real numbers. Wonderful. All right, next question. And then this next page is my last page. And we got two more questions. And really the key here is paying attention to what kind of root is being taken. So number 7 is exercise 380. We have this function called, capital F of x equals the fourth root of 10 minus 7x. So again, it's an even root. Even root. So the radicand, 10 minus 7x, has to be greater than or equal to 0. And then we're solving this, for x. So I would subtract 10. Now divide by negative 7 would flip the symbol, so x is less than or equal to 10 sevenths. Positive 10 sevenths. Right. And that tells us our domain, 1 in 3 sevenths, or less is a value I can plug in for x. Anything greater than this, I'd be taking the fourth root of a negative number, which would be non-real. Right? I wouldn't have any ordered pairs to plot. Right, so the domain of capital F here is, I can plug in anything for x I wish, as long as it's a number less than or equal to 10 sevenths. So that's one way to put it in set builder notation. The other way is with interval notation. Now you can draw, now this time I'm not going to draw a picture on the number line. You can do that if you wish, but anything, this is less than or equal to 10 sevenths, so 10 sevenths and everything to the left on the number line, so to negative infinity. So from negative infinity up to 10 sevenths, parentheses on the infinities, and 10 sevenths is in the domain here, so a bracket. So there's what it would be in interval notation. And then once again, I'm going to take a look at this function on the Desmos site. Just typing in as is, it was capital F of x, right, equals. Now instead of looking for the fourth root, that nth root button, right, I'm just going to put the radicand, 10 minus 7x in parentheses, and raise it to the 1/4 power. Remember, the 1/4 power was the fourth root. And look, see, the graph doesn't go to the left and all the way to the right. It stops at this point here. 1.429, right? That's 10 sevenths. Right, let me show you. 10 divided by 7 rounds to 1.429. It's 1.42857, 1.42857, and that 1.42857 would keep repeating. But yeah, so this is x equals 10 sevenths, and then every point on the graph has an x value, less than 10 sevenths. Negative 6.19, negative 7.16, right? All these points on the graph have an x coordinate less than 10 sevenths, and this point has an x value equal to 10 sevenths. And then everything, to the right of 10 sevenths on the x-axis, see, there's no graph over here. Because if you plug anything greater than 10 sevenths, you'll be taking an even root of a negative number, which is not real. So it wouldn't correspond to any points on this graph, right? The x and y axis represent real numbers only. Wonderful. All right. And my last question is easy. All right. State the domain and put it in interval notation. Number 8, exercise 382 from the text. We have this function g of x equals the fifth root of 6x minus 3. Odd root. So just like the cube roots earlier, you can take an odd root of a positive number, of a negative number, of 0, right? Anything, any real number. So as long as there aren't any denominators, which there aren't with variables, right, you're good. You can use anything you want. So like in questions 5 and 6 with the cube roots, the domain of this function here is, I can plug in anything for x I wish, any real number. I'll just say x is real. The domain is all real numbers. I can plug in whatever I want for x. There we go. And the interval notation for this we have seen. The domain, so the domain of this capital G function is, from negative infinity to positive infinity, right, with parentheses on those. You can plug in any number at all for x, and you will get a real number output. It will correspond to some ordered pair on the graph of this function, which, I will take a look at now. All right, let me enter this function we were given. It was g of x equals, and then again, instead of the fifth root symbol, I'm going to put the radicand in parentheses, 6x minus 3, raised to the 1/5 power, and there you go, right? Here's your fifth root. And notice again, I can zoom out, zoom out, zoom out. There's always graph, right? There's no gaps, there's no holes, there's no area where there's no graph, right? And every single x value is used, right? All these -20, -9, -8.1, right? All the way from left to right, forever and ever. All right, so the domain of this function is, all x values, all real number x values, all real numbers. Great. And that's it. All right, so I'm hoping that, watching me go through these 8 questions here help you in some way when you're working on finding the domain of a radical function on your own. And thank you very much for watching.